Hello everyone, welcome back to another lecture. This time we're going to talk about sensation and perception and some aspects of how the two go together and how they interact and relate to each other. When you think of sensation and perception, the reason we put them together is because sensation is the first step and perception is the second step. In how we process the world. And they're both needed, and their relationship with each other is quite interesting. So the definition of sensation from your textbook, the process whereby or by which sensory receptors and the nervous system receives and represents stimulus energies from our environment. So sensation is information coming in. Perception, on the other hand, is the processing and organizing of that information, sensory information, enabling us to recognize meaningful objects and events. So sensation is the actual data that comes in. Perception is how we experience the data. So with sensation, the brain receives the input from our sensory organs, our ears, our eyes, our skin, the taste buds on our tongue. Perception is what the brain takes those sensory inputs and organizes them and delivers to us an experience. That is the relationship between sensation and perception. Now, just a couple of observations here. Historically, as we've studied sensation and perception in psychology, one of the mistakes we've made is that we've confused sensation and perception. And while we look at them together, they are distinct and distinct enough that we sense things that we don't perceive, and we perceive things we don't sense. So we'll get back to that idea as we go through our chapter. So when we take information from our world, we can organize it into what psychologists have referred to as bottom-up or top-down processing. So bottom-up processing is when I take incoming sensory information and my brain organizes it and processes it and then delivers me an experience. So what am I seeing? I'm looking at something and my brain organizes what I'm seeing. That would be bottom-up processing, because I'm starting with the sensations and the sensory experience first and then organizing it. Top-down processing would be the other direction, and simply I'm starting with my perceptual past, my perceptual memory, and my expectations about what I should be seeing. In other words, I'm looking at or I'm taking in the sensory information, but I'm organizing it according to stored data or stored information in my brain. We're constantly doing both of these, bottom-up processing, particularly when we see or experience something new. But once we see or experience something and have memory and storage, then we tend to perceive new sensory information in light of the old sensory information. And that's an important distinction, that once we have experienced an object, a situation, or event the first time obviously we're highly dependent upon bottom-up processing. But once we have, can I put this term, experience with something, we never we don't forget that experience. There's always some top-down processing coming in. In other words, I'm experiencing this, and our brain says it's kind of like when you were experiencing something else. So both of these things are almost opposite sides of the same coin as we seek to make sense of the world we live in. Now, take a look at this image on a bottle. Most of us as adults look at that, and we see a clear image on there of what looks like a man and a woman. But when you show this picture to most children, particularly under age 10, they don't see what you and I see. Rather, what they see are a bunch of dolphins. it's a good illustration of how our experience begins to shape how we organize our sensory perceptions. So think about this. Most children don't have much experience with, I don't know, I guess this looks like a man and a woman kissing and they're naked. Hopefully they don't. They do have experience, at least most American children, seeing dolphins. And so when they look at this, again, they see the dolphins. When you and I look at this, maybe some of you saw dolphins. I did not see dolphins at this. And so it's a good illustration of the difference between sensation, because whether we're children or whether you and I are looking at this, all of us are looking at the same thing. The same sensory information is coming into our brains. But the perception of that sensory information is going to be affected. And again, just a simple example, it's going to affect what we actually see. And in this particular case, whether we're younger or whether we're older, and the various experiences of being younger and older is going to shape. Do we see dolphins, 6, 7, 8 dolphins, or do we see basically two naked people kneeling down and kissing? It's a good example. How about this one? A bunch of dots. We're looking in front of us at just black and white. Semi-random dots. I don't know if you see anything. The sensory information, whether you're seeing something here or not seeing something here, we know that if we cue people to think of something as they look at this, then most people are likely to see something. So if I say, tree, that's in your mind, and your auditory cortex picks up the idea, picks up the sound tree, and it prompts you to think of trees. And now as you look, it becomes top-down processing, because you're cued, or you're almost triggered to look for a tree. I still don't see a tree. Do you see a tree? I looked at this for a while. Sidewalk, I guess. Now, the dog I do see, and particularly Dalmatian, I see what looks like a dog sniffing the ground, and because the picture is in dots and little pixels here, it looks to me like there's a dog sniffing the ground, and that dog has spots on it. So I see the Dalmatian. Now, did I see the Dalmatian before? Yes, I did, because I have seen this image before and know what they were cueing. But ask yourself, when you were first looking at this, did you see anything at all? Now that you have the words dog and Dalmatian in your mind, which quite frankly are the only things I was able to see in here, I was clearly able to see them. And that's another good example of top-down processing. Now, we have all over our body specialized sense receptors. These are specialized neurons. We'll talk about that in a minute. That pick up information in my external and in some ways internal world, and send that information through a process, a 3-step process, to my brain. This may seem like a ridiculous thing to say, but we don't really see with our eyes. We actually see with our brain. We don't really hear with our ears. We actually hear with our eyes. We don't really taste with our tongue. We taste with our brain. What am I saying here? Well, your tongue and your skin and your ears and your eyes, these are all, again, places where there are specialized neurons clustered together to give us information about the world. And clearly that information is sent from wherever it's taken to my brain. My brain puts it together and organizes it, and then delivers me an experience of what I'm seeing, an experience of what I'm tasting. So the 3 steps as information goes to the brain is, first of all, reception. This would be the sensory cells the particular sensory cells. So for instance, rods and cones at the back of my eye, the taste buds on my tongue, and receptors in my skin for temperature and pain and pressure and so on and so forth. So those sensory receptors pick up the information. Then that information has to be, if you will, translated, or transducted is the term we use here, from a light wave, for instance, if we're talking about eyes, to a neural impulse. And that neural impulse leaves my eyes by way of the optic nerve. It crosses that optic nerve crosses and goes to my left and right hemisphere, and that transmission is basically done via the, in the case of seeing, the optic nerve. In the case of other specialized sense receptors, different nerves. So sensation, even of itself, is somewhat of a complicated process. First of all, again, reception, then turning this information into neural, into neural bursts, if you will, and then the transmission, the delivery to the brain. Once it gets to the brain, we have the process beginning of perception. Now, psychologists for over 100 years have been studying sensation and the perception aspect secondarily. And so a couple of just general concepts we have to talk about. The first is what we call absolute threshold, which is defined as the minimum level of stimulation needed to detect any external stimulus at least half the time or more. So absolute threshold is just the point at which, again, if we took a light, if we took a taste, if we took a smell, but the point at which a little over 50% of the time you can absolutely detect a stimulus. And below 50%, we refer to that, can I say, perception as subliminal. Now, subliminal experiences do exist, and so you have to think of subliminal, subliminal. It's below a certain point, a liminal line, and but clearly the difference between subliminal and supraliminal, or that absolute threshold, doesn't remain constant, and it differs from person to person. And clearly, a 49% versus a 51% isn't going to be all that different, but we have to draw the line somewhere, and this line is called the absolute threshold. Now, absolute thresholds are ironically not always absolute, and so you may think, again, I'm talking in circles, but signal detection theory is simply an approach that attempts to understand how absolute thresholds work. And if it was absolute, it would be absolutely that case in every situation. But what we know about absolute thresholds is that my ability to cross that threshold and perceive that sensory experience more than 50% of the time is going to be dependent on a wide range of factors, what we call background noise. Psychological factors such as my past experience, what I'm expecting, am I happy, am I sad, what are my motivations, have I just gotten a lot of sleep, did I just eat a big meal? All kinds of factors are going to affect and mitigate what the absolute threshold is. So ironically, the absolute threshold is not all that absolute. It's constantly changing. It's more of a theoretical construct for drawing the line between 50% and below, and 50% and above. Now I want to give you some illustrations of that in a little bit. The just noticeable difference is a concept which almost always goes along with absolute threshold, and it's simply this. When I'm perceiving, when I'm having some sensory experience, so let's say that I have a backpack that that I have on my back, and it has one brick in it, okay? Now, I'm perceiving the weight of the backpack on my back. Now, do you think if I added another brick, doubled the number of bricks, that I would be able to notice that it got heavier? Yes. Why? Because the difference between one brick and two bricks is double. Now, how about this? Let's say I had a backpack and I had 100 bricks in it. Now, again, in that situation, if I added one brick, would there be a noticeable difference between the experience of 100 bricks and 101 bricks? Probably not, okay? So that's this idea. What is the, again, J&D, just noticeable difference in any experience that I can relate where I'm aware that the experience has somehow changed? And Weber's law is a law which, again, you'll read about or you already read about, which refers to this principle that for two stimuli to be perceived as different from each other. In other words, for the J&D to kick in, they must differ by a constant, and that constant, it's a constant minimum percentage, not a constant amount. So the constant amount would be one brick. But again, noticing the difference between 100 bricks and one brick, not going to happen. But a percentage, it would only be 1% if I was adding one brick to 100, but it would be, again, 100% if I was adding one brick to just one other brick. And so that's the J&D and what Weber's law says in relation to that. Now, as we already mentioned, another complicating factor here has to be what psychologists have studied called sensory adaptation. And let me just try and describe it. When you and I are bombarded in a constant way by a stimuli, let's just say the sound of an air conditioner, or the feeling of my shoes on my feet, or the maybe sensation of a beard. What happens is our body adapts to that constant sensory stimulation. And what do we mean by adapting? We get used to it. And when we get used to a constant, we actually stop perceiving it. So again, if I could just ask you to concentrate for a second on your right foot and how your foot feels inside of your shoe if you're wearing shoes. Well, you can feel that. You can wriggle your toes. Were you able to feel that before I said that 2 minutes ago? The answer is yes, you were feeling that, but you weren't consciously aware of it. You weren't paying attention to it. Why? Because it's a constant stimulus. We ignore it. Or again, when you first turn an air conditioner on, it sounds very, very loud. But once the air conditioning's been on for 2 hours, it's like you don't even hear it. You're not paying attention to it. You're not saying to yourself constantly, the air conditioner's on, the air conditioner's on. No. You'll only notice the air conditioner if it stops, turns off. Then all of a sudden, you become aware of the sound of the air conditioner because it's no longer there anymore. So sensory adaptation is simply the concept that we stop perceiving or we greatly reduce our perception of environmental stimuli that are constant, and rather we tend to focus on environmental stimuli that are novel or new. We're constantly looking for change in our environment, and this is very adaptive for us. That's why it's called sensory adaptation. But it's adaptive in that we don't have to waste our processing brain on constantly dealing with stuff that remains constant. We can focus upon changes in our environment and again, important new things that arise, and let the things we're getting used to. If I could give you another example of sensory adaptation, we've all had the experience of maybe being at the beach or being by a pool, and we're sitting in the sun and we're hot. So when we first jump in the water or run into the ocean, it's cold. It's really cold. And of course, sometimes we'll have to, scream as we get used to the water. Well, once we've been in the water, splashing around for half an hour or so, the water doesn't feel cold anymore. Again, why? It's the same temperature it was when we got in it, but we've become adapted to the temperature of the water, and now we're no longer paying attention to it. Now, if the water's really cold, I mean, if it's December and you're one of those polar club, polar bear club members, the people that go swimming in December on Coney Island. Well, I don't know if you're I don't know if you're going to have time to sensorily adapt before you turn blue and freeze, but that idea I think you get. Okay, a perceptual set is something we expect to see. So here's where experience comes in and begins to shape our perceptions. Here's where, if you have seen the picture in front of you before, you probably were told, or you read it, saw it in a book, or saw it on some website, and you probably read the caption, which basically said, "This is the best photograph we have of the so-called Loch Ness monster," right? But let's say I showed you this this image in front of you, and you were from, I don't know, Papua New Guinea, or you were from a small island off the, the coast of, I don't know, Chile, and you had no access to media or wherever or anywhere. You wouldn't look at this and see the Loch Ness monster. You would look at this and maybe move your head back and forth, and depending upon your own experience with water or tree branches. So what happens here is that once our experience has created what we call an expectancy set, a perceptual set. In other words, once we've learned what to expect, we tend to see images, or we tend to see the world in a way which conforms to my expectancy. This is why you've all heard the saying, can't teach an old dog new tricks, or my mind's made up, don't confuse me with the facts. Because once we actually perceive the world a different way, it's very hard for us to perceive it a different way. We either have to be extraordinarily open and put effort into trying to see it a different way. This is why creativity tends to be something that is associated with being younger as opposed to being older. Because the longer you've been living, the more experience you have of dealing with the world a particular way, it becomes harder and harder for you to step outside that, again, perceptual set and see things differently. Although when you're younger and you don't, you haven't had a lot of experience that things should be this way or you should experience it this way, you have a greater opportunity to, again, exercise a kind of creative application of, or creative perception of what you're seeing in terms of sensation. Again, if I was looking at this, if I believed in UFOs, chances are I would see UFOs. If I had never heard of UFOs and I came from, again, some place in the world or some culture in which the idea of UFOs was never broached and never talked about, I wouldn't see UFOs. I would say, well, those are weird looking clouds, because I might have experience with mountains and the blue sky and looking at clouds sometimes. And so expectancy tends to the shape what we see. So, for instance, if I could give you one other example, let's say I said, I want you to think of a 6-letter word that starts with H. Okay, and I'm going to give you the first three words, and I want you to 3 letters, and I want you to complete them. Well, and I said to you the first 3 letters are H-A-M. Now you might say, think about it and say hammer, H-A-M-M-E-R. But let's say that right before I gave you this little quiz, I was asking you about Shakespeare and what your favorite Shakespeare play was, if you have one. And then I said, 6-letter word starts with H-A-M. Well, in that particular case, you might say Hamlet as opposed to hammer, not because it's set up not because it was a conscious attempt to set up an expectancy set, just because it's recently in your mind. And so we do tend to see what we want to see. We are, ladies and gentlemen, like old dogs who find it hard to learn new tricks. This image you have in front of you, again, we can slightly change it. On the one hand, if you look on the left, if I say, look at this picture and you should see an old woman. On the other hand, if I said, look at the one on the right, you should see a young woman. Again, as you look at both of these pictures, they're the same, a couple of details. You know, we have the earring and the necklace on the right, and the kind of slice in the woman's mouth. But clearly we can get you to respond to an old woman or a young woman, even if we give you this. It's distinct enough and ambiguous enough that if I just said look for the old woman or look for the young one, if I just create an expectancy set, just about every single person that is told look for the old woman is going to see, you know, this face of this woman with this kind of babushka. Just about every single person is going to see, you know, the profile of a young woman kind of looking away, you know, to her right, if we prime it that way. So the moral of this story, or what I'm trying to get at, is that perception is a different animal than sensation. It uses sensory information, but then, depending upon any number of things, creates and delivers to you an experience of something. This is why two people can be in the same exact situation and have two different experiences. And we've all had that. You know, two people are listening to a song. One person loves it, the other person hates it. We should also add that the context of one's situation or experience sometimes shapes how we perceive something. So to give you kind of an obvious example here, look on the left and you see that purple dot in the middle, and then look on the right and you see the exact same sized purple dot. But of course what happens is the context of the purple dot changes our perception. Indeed, for most people, the perception of the purple dot on the right looks bigger than the perception of the purple dot on the left. And yet, the exact same sensory information about the size of those two purple dots going into your brain remains exactly the same. Okay, so what I'd like to do with you now is to give you a pop quiz. So again, if you have a piece of paper and you want to do this, I want you to just spell the following 6 words, okay? And if you don't feel like doing it, you can just go along. But the first word is double. Single, you've heard of, spelled double. Okay? Second word is pair. The third word is apple. The fourth word is pear. The fifth word is payee. Payee. And the sixth word is pair. Okay. So, how'd you do on your spelling test? Well, this is an interesting research study which found that the 3 words, the second, fourth, and sixth word, was pair, pair, and pair. Okay? But research has found that if you say apple and then say pear, most people are going to spell pear P-E-A-R, as in a pear, a piece of fruit. When you say double and then the next word you say is pair, most people will spell it P-A-I-R, like a pair of eights or a pair of kings. And again, way less common If you say payee and I say pair, and again, I don't know if you would ever get that. Most people would write down payer as in pay, P-A-Y-O-R. Now again, what's simply going on here is the context of the sensory information coming into your brain tends to shape your perception. So when I say double and I'm told to spell pear, I tend to see pear not as a piece of fruit, but the sound as indicating two. And these are two examples of visual context and auditory context that you can, I think, see. There are so many other experiences, again, that show the effect of emotion and physical state and motivation, any number of other things. So, for instance, when you're tired and you have to estimate the distance of something, people that are tired estimate the distance as longer than people that are not tired. If you're shooting a crossbow, and I've never done that, when the crossbow is heavier, people say that the target is farther away than a lighter crossbow. And on and on and on it goes. A hill looks steeper when you have let's say you had that heavy backpack with 100 bricks in it, or after you've listened to sad music, or when walking alone, than when you have no backpack, or you're listening to joyful music or intense music, or when you're walking with somebody. So the whole field of sensation and perception, and I don't have time in our lecture here, simply says that our perception is hugely affected by, well, literally hundreds of different variables. And so you'll just have to take my word for it as we move on here. That looks really good if you're hungry, although I'm not a big ice cream fan. Okay, let's just talk a little bit about some technical aspects here. Our visual sense, and I'm going to go over this really quickly because you have an opportunity to read this a lot more slowly, but think of how amazing it is to see something. I'm sitting in my office. It's a beautiful day out. It's sunny. It's kind of windy. I can see clouds, the beautiful blue sky. There's a tree in front of my window, and although I can't hear the wind, I can see the leaves. It's just it's quite beautiful. So clearly, our visual sense, which I would really, really not ever want to go blind. I mean, as if anyone would, but I love looking at stuff. I'm sure you do too. But our eyes use the light waves that are out there, and clearly our visual, our spectrum to human beings, our eyes can see only a very, very narrow band of light waves. There are other animals and organisms that have a much wider span. And of course, there are others that have a much narrower one. But on the basis of the spectrum that's visible to most human eyes, our brain uses those light waves and delivers to us all the beauty and sometimes not so beautiful things that we see. The eye is a very complicated thing, and again, light enters first of all through the cornea, and then goes through the pupil, and the iris is the part of your eye that has the color, and then it is focused and then turned upside down, literally on the lens, and those light waves hit the back of the eye, which is the retina. The fovea is the middle of the retina, and the retina is clustered with two specialized receptors called rods and cones. It is quite an amazing thing. Think about this. We perceive everything upside down. Think about this. Sensory information goes into our eye upside down, and yet we perceive everything right side up. There are these glasses you can put on which turns everything upside down. And it takes a couple of days for you wearing those. But after 48 hours or so, you'll wake up on the third or fourth day, and what'll happen is you'll actually now, with those glasses on, see everything right side up, even though the glasses are turning everything upside down. And in other words, your brain will accommodate to switch your whole world. And then when you put those glasses down, it'll take you a little while for your brain, maybe a day or so, to switch everything back right side up. It's quite amazing. The rods and cones that are in your eyes, they specialize in different types of information. And so you can see that these ganglion cells here pick up the information, and it is translated into neural impulse, and then goes again to the visual cortex of the brain, which is in the back of your brain, and there's a blind spot exactly at the back of your eye where the optic nerve leaves, but your brain just fills that in. You and I don't experience our blind spot ever, but I promise it is there. The rods are way more common than the cones. Rods, you can see you have about 110 to 130 million. You only have 6 cones. The cones tend to be clustered right smack in the center of your eye, whereas the rods are kind of on the periphery. The rods, you need a lot more of those because they are specialized for when it's darker or for very, very dim light. Cones are specialized for very light, intense situations, so that we've all had the experience when we're maybe going to the bathroom in the dark, or there's no light, the lights go out, and we're staring at something but we don't see it because there's not enough light. If you're ever in a situation where there's very, very minimum light, and you want information, don't directly stare your eyes at it. Actually move your eyes a little bit away from what you want to look at, so that your peripheral vision is, so that whatever you're looking at is in your peripheral vision. You'll actually get more information to your brain about that. These rods and cones are specialized receptors. We have to, in the first couple of years of our life, learn that there are some things in our environment that remain constant, and yet they always look different. So color and brightness, shape and size are the 4 constancies. Now I just want to mention them briefly. Imagine that you took, like a phone, and you held it in front of a baby far away as opposed to 3 inches from their face, and you turned it flat, or you turned it, one way or the other, to the baby and to you and I. The sensory information coming into our brains changes. The phone, quote unquote, looks bigger when it's closer. It looks really, really teeny when it's far away. So on the basis of our experience in the first couple years of life, we learn that there are things that stay constant, and these are the 4 everybody has to learn. The first is color. Color stays the same regardless of how it looks, whether it's again in dim light, whether it's in a different kind of context. Blue is blue is blue is blue. Now, if you looked at the example here on the right, the blues actually look different to us. We almost have to fight the notion of perceptual constancy, but colors stay the same. The brightness stays the same too. That we have to learn that square A and B, believe it or not, are the exact same shade of gray. And B looks lighter, doesn't it? But they're exactly the same shade. It's just, and again, what we're doing is we're fiddling with this. Let me go back. There you go. We didn't change anything. That's certainly shading. So we have to learn. And so all these things I'm giving you are examples where we mess with our notions of constancy. Again, shape, that the shape of an object is going to stay the same. Like a door is a good example. The shape in terms of the actual information coming to your brain changes, but we have to learn a door isn't morphing into different shapes when you open it as opposed to close it. And then clearly size. This is a famous room created by an ophthalmologist named Aldebert Ames. And again, the lines in the room are set up to make this person look bigger or smaller. So we can trick our notions of constancy. But these four things always remain the same. Let's talk a little bit about hearing, because we use sound waves instead of light waves to hear, and sound waves clearly have three properties. The first is the frequency. This is the length of the wave. In other words, from the top of one wave it goes down, and then to the top of the next wave, and this is what gives us the notion of pitch. Then there's the amplitude, the height or intensity of the wave. This gives us the perception or experience of the volume. And the last thing is the complexity of the sound. And again, whether it's a simple tone or as with very interesting music, music is interesting to us because it's kind of a layered sound. And again, there might be something very beautiful about just hearing a piano alone playing. That would be more of a simple tone, as opposed to an orchestra in which a piano is also playing. It'd be way, way more complicated. Hearing is one of those things we just don't think much about and we take for granted. But it's pretty cool how this works. Sound waves are directed into your ear by this little kind of like radar dish you have on either side of your head. They enter into this little space called the auditory canal, and they are directed toward in about half an inch or so, and there is the eardrum, which vibrates ever so slightly in response to those sound waves. There are three little bones that are attached one after the other from the eardrum into the semicircular canals and the cochlea, and those are the hammer and the anvil and the stirrup. And so think about this process as you have a vibrating eardrum, and now those vibrations are passed along and eventually come to the cochlea, which is filled with fluid. And this cochlea has little hair on the walls that respond and move to the vibrations, and those receptors attached to the hair cells take the vibrations and turn them into neural pulses, and again, that goes out to the brain through the auditory nerve. It doesn't have far to go. Your brain is right there. Again, the complexity of this is kind of amazing, particularly when we're hearing amazingly complicated sounds. But that's how this process works. Again, sound waves come in here. We have a vibration, hammer, anvil, and stirrup. Here's the stirrup. You can see it looks like a stirrup. It's attached. It vibrates, and this fluid that these little hair cells are in vibrate, and we have the attached nerve cells here, and they're bound together, and they allow you to experience the sound of my voice. Touch is kind of interesting. Touch is, for us as humans, is hugely psychological, obviously. It is a sense, but from the very earliest moments in life, touch isn't just sensory. It becomes very, very perceptual early on in life. Think about this. Let's say you're sitting in the library and someone comes up to you and hugs you. Well, that's a weird experience because we almost don't know how to respond to that hug till we know who it is, and we'll turn around right away. And if it's someone we've never met before, that's a little that the perception of that touch is going to be very, very different than that it's someone we know and love. So touch is hugely psychological very early on in life, and has a lot. Well, it's freighted with meaning in terms of attachment and comfort and support, and again experience. The world is full of people that, for whatever reason, have experienced touch or certain kinds of touch in an abusive way or in a horrible way, and their perception of touch is very, very different than if you haven't experienced it in that way. There are 4 aspects to touch: pressure, pain, and then depending on, we could say warmth and cold, or we could combine those two into temperature. And you have, again, specialized receptors all over your body for those. They are clustered more in certain parts of your body. So if you were to get a tattoo in some parts of your body, the process is going to be way more painful than in other parts of the body. There are a lot of these specialized receptors, for instance, right around your lips, your mouth, your lips, very, very, very sensitive. Clearly, our genitals are packed with neuroreceptors, and other parts of our body, for instance, the back of your calf at the back of your leg, your buttocks. For most of us, maybe the certain parts of our back, not so much. And again, we can fiddle with this. It's kind of an interesting experience that when you grab, say, 2 pipes that are intertwined and one is hot and one is cold, that it's really, really weird. When you grab it, it almost feels like you're grabbing wet pipes. They're dry as can be. I don't know who discovered this or why, but touch, again, is pretty important, and I wish you'll have to take a class on sensation and perception for you to get the rest of this. Taste, again, is something that unlike temperature, unlike the sense of touch, your tongue is doesn't specialize any part of your tongue, but again, you have specialized neuroreceptors, particularly for 5 tastes. Most of us know the salty, the bitter, the sweet, and the sour, and the 5th one is what's been called savory, or umami, U-M-A-M-I, umami, which is a kind of a meat, like a meat taste, and all the combinations of those things. But clearly taste is such a, the sensation of taste is there, but we quickly learn to like taste. I remember the first time I tasted black coffee. I remember almost spitting it out of my mouth. When I tasted it, I thought, that is the nasty. Why would people ever like coffee? But here's what happens: we gradually learn to like even bitter things, or the taste of red wine, for instance. I think I was 12 and I was at a friend's house the first time I tasted red wine, and again, I almost spit it out at the table because it's kind of nasty taste. So the perception of taste certainly is very different than the sensation of taste. If I could throw in a little of research that has really nothing to do with this, even before we're born, we're already learning what tastes we like, because the food that our mom eats while she was pregnant with us actually flavors the amniotic fluid that we're floating in before we're born. And since in the 3rd trimester, all of us are drinking amniotic fluid already, even before we're born, whatever our mom is eating is already shaping our later taste preferences, and tons of research has been shown on that. Again, the sense of taste is one in which top-down processes come in, as we've already mentioned it, that I learn to like, for instance, sushi, or I learn to like the taste of something that maybe as a kid I would thought was disgusting or icky, and that may be because this food is associated with my childhood, or this food is associated with celebrating certain kind of holidays, or I may have liked a certain kind of food, but then I get horribly sick and I spend 2 days throwing it all up. And again, my top-down processing may change, at least for a short period of time, about that particular food. Our sense of smell is the sense that human beings do have that tends to be the weakest for us. We do have all of these specialized receptors in our epithelium, which is the upper cavity of our nose, called the olfactory bulb. And again, there are 350 different ones, unlike again, touch, which is 4, or vision, which is just 2, and different combinations of those things really gives us the opportunity to be able to distinguish upwards of 10,000 different smells. But as human beings, we don't use our sense of smell, at least most people would agree, very, very much. And so our perception of smell tends to be focused on pretty much strong smells. Certainly if something is extremely unpleasant, or something is extremely pleasant. So for instance, the smell of chocolate chip cookies baking, at least for me, is a pleasant memory. So these are just molecules in the air, and that's the sense of smell.